Welcome to the 23rd common session of Sunoikis Digital Classics 2017. Today is our last session of this long semester, and today our guest is Thomas Köntges from the University of Leipzig. So Thomas Köntges is contributing for the first time to Sunoikis. So Thomas, welcome to Sunoikis and thank you for this class. So you have today the topic is topic modeling of morphologically complex languages. You have the class outline on GitHub, including the slides, and also the description and everything. But now I think we can start. So Thomas, welcome to Sunoikis.
Hey, yeah, thank you. Thanks for having me. Yeah.
Okay, good.
Okay, good. I will just share my screen. Okay. You should be.
Yes, I can. Yes, I can see your screen, and you can start. It works.
Okay, good, perfect. So today I'm talking about topic modeling of morphologically complex languages and why this is slightly different than topic modeling modern languages or morphologically less complex languages like English or German. I will also introduce you to the method called topic modeling and try to give you a very classicist-friendly introduction to topic modeling. I'm a classicist myself, and I'm a classicist myself and self-taught in that area. But now I'm an assistant professor in computer science, and apart from corpus creation and digital and researching textual transmission, I'm mainly into information retrieval using ancient texts as well. And the method I'm using is topic modeling. So the structure of the talk is outlined in the GitHub repository is a short introduction to topic modeling. Then I will talk about how you could use the results of topic modeling in teaching. I will speak about the challenges of topic modeling using historical languages, and I will present to you a use case where we topic model around 30 million words of Latin and summarize quickly of what we learned from that and what are the first first provisional outcomes of that. Finally, I will also introduce you to a little application I've written. It's a topic modeling graphical user interface where you can do topic modeling yourself for any language, although the most fun you get out of it if you use Latin or Greek, but it should work for any language, any historical language and any modern language as well. And there's no coding involved, so everything works via a graphical user interface. So let's start with why we even care about topic modeling or methods like that. For one of the few times in the history of humanity, we actually know in which period of time we are living. And we are living in the digital age. And we already also know since when we are living in the digital age. That is 2002, because in 2002, for the first time, we saved more information on digital means instead of analogically. And by 2020, we have so much data that it embeds 5 times more data than there are grains of sand on the beaches of the Earth. To give you another example, in 2012, we produced, as humans, 2.7 zettabytes of data. That is around 550 editions of Homer, Iliad and Odyssey per person on this planet per day for every year. So it's lots and lots of data is created. Most of it at the moment is surveillance data, but also in the humanities, the amount of data is increased rapidly. There are several thousand publications on JSTOR alone, and not to mention Google Scholar or all the monographs on Google Books, or the text digitized by the Köntges Digital Library, the Open Greek and Latin project, the CHS, University of Iowa, and so on. So there's lots of text out there, and nobody can read all the text. It's physically not possible to read all of Latin literature. Even if you would spend every hour of your working life reading Latin literature, you wouldn't finish all that is written in Latin. And so how do we select what is interesting to us is often very biased, because we don't actually know what's in some of the text that is lesser known, but it might still be relevant to our research topic, be it which ideas the church fathers had in Latin, or gender theory in late antiquity, or anything like that. So how do you find the texts that are relevant to your research topic? And sometimes you don't even know the text very well, especially when it comes, especially if it's something slightly off the beaten track, something slightly different than Ovid or Virgil or Plato or Homer or something like that. So one approach to actually find the interesting bits is topic modeling. As I said, as our collective knowledge continues to grow, it becomes more and more difficult to find what you're looking for. And topic models, instead of just being a search and link approach, they're trying to find a hidden thematic structure in large corpora of text. And that's without any prior annotation or any prior labeling of the text. And even better, you can zoom in and out using topic models by setting the number of topics in the beginning, but more to this in a little bit. Topic modeling is a method to find clusters of words in large bodies of text. So it's a method of statistical inference that doesn't look, not just simply looks for co-occurring words, but it looks for co-occurring word fields. So, and in that way it's very handy, which means topic modeling is very good to differentiate between homonyms. The English word panel can mean the panel of an artist, or the panel that decides if someone gets a scholarship or not. And topic modeling can differentiate between those two. That's how a topic model looks. It's an LDA visualization from R, and it's actually a topic model that I produced for the National Library of New Zealand. And it's a topic modeling base of 100,000 abstracts of articles written in English and partially Maori that are saved by the National Library. And even if you have no idea about New Zealand or no idea about those articles, you know the topic 4 that is selected if you look at the word court, act, law, legal, decision, case, rights, justice, and so on. You know it's a topic about legal cases. And all of those topics are meaningful, and you can look at all of those topics. Topic modeling itself does not only find those topics, but if you, for example, would have a letter corpus, it's possible that you have a topic that consists out of greeting formula. So dear, to whom it may concern, hello, and so on. So it's not always thematic topics. In that way, what the machine understands as topic is different to what we humans understand as a thematic topic. There are definitely topics that are just important for the structure of the text itself. So how does it work? One very easy algorithm is the latent DIRICHLET allocation, developed by David Bly in the early noughties. And it's using a simplification model of how the documents, how the text in a corpus were written, were created. It says that it pretty much implies that the texts were created using a Dirichlet distribution. So I don't want to become too mathematical here, but in a Dirichlet distribution, we have a set of topics, and we choose words, we choose topics for each document, and then we randomly take words out of this chosen topics and throw them into this document until we have written our text. It's a little bit like, maybe like Pollock painting a picture, not quite obviously, but it's an oversimplification of how documents really are created. And one of the reasons why this is possible is the back of words principles. In the 1950s, Zelig Harris said that the order of the words are not so much determined in order to find out what a word actually means. What is more important is the neighbors of the words and in which the context in which the word appears. And that, of course, works very well for English, but for Latin and Greek, it's a bit more challenging, and we will talk about that in a few minutes as well. What is important, though, for the LDA algorithm is that each corpus has words from a number of known topics, which means if I want to start my topic modeling algorithm, I always have to set the number of topics. So I have to say, in this corpus, we find 20 topics. In this corpus, we find 50 topics. In this corpus, we find 100 topics, and so on. And of course, you might say, well, how do I know what is the best number to set here? And that's, in fact, one of the research problems topic modeling has. The University of Vienna looks quite precisely in how to set the perfect K, Ks being the number of topics for each corpus. I have a more relaxed approach to things, and I'm not the only one who has that. You can, of course, there are methods of how you can find the perfect K, but what is the perfect K often depends on your research question and not just on a perfect K of the corpus itself. For example, when we go back to the New Zealand topics, when we increase the number of topics, we had one royal family topic. But if we increase the number of topics, suddenly those topics split up into smaller topics. There was suddenly the royal wedding and the royal baby and Prince Charles's visit to New Zealand. So increasing or decreasing the number of K can be a research tool for the humanities scholar in order to find the topic in which they're interested in and score the documents in the corpus based on that particular topic. I hope that's clearish. It's a little bit like photographing. If you have an auto zoom in the camera, but it's not always best. If you want to get clear shots of a small bee on a flower, you might want to switch to the manual focus, and then you have a much better focus on what's going on. So we do not know which words belong to which topics. We only have the distribution of words. And because of this, so in LDA, as I said before, we're looking not at the word itself, but we're looking at the surroundings at the word. So we look with which other words does the word panel occur in a document and over the whole corpus. And because of that, we can actually differentiate between the 2 or 3 or 4 or 5 different meanings of the word panel. So the central goal of topic modeling is to automatically discover the topics from a collection of documents. And the central inferential problem for LDA is to determine the posterior distribution of the latent variables given the document. So how many topics, how is the probability skewed that one document consists out of how many topics and so on. But you as a scholar have influence on that, obviously. That was probably fairly difficult to understand, so I try to give you a better example. And a good example is probably how to choose a table at a conference. So here we have a conference. So those papers on the bottom of the screen, the talks people are just exiting, and the round gray bits are conference tables. And you see here 2 people on this table talking about sports and politics. He has 3 people on this table talking about classics and movies, and he has 1 person, that's mainly me, talking about classics and topic modeling. So, and the people are coming out of these papers, and they will, with a certain likelihood, go to either this table, or this table, based on which are the interests, and the interest is indicated by the paper that they have just given. So that is pretty much the generative process of the Dirichlet distribution, simplified in a way. So, but what we do is a Dirichlet allocation, a latent Dirichlet allocation. So we do have the tables, and we have the people on the table, but what we don't have is we don't know what they're talking about. So we only see the people, we see the number of tables, and we see the number of talks they are coming out of. And we try to reconstruct, by looking at this and by looking at the distribution of people, we try to reconstruct this process. And that actually then helps us to name the talks and so on. So how do we do that? How can we reconstruct from this? Yeah. When it comes down back to words in a corpus, we just randomly assign a topic to each word in each document. So for each document in the corpus, we assign to each word a topic. Yeah, and randomly. This word is topic 2, this word is topic 3, and so on. The 5th word is topic 9, the 11th word is topic 17, completely randomly. And then we go from, our algorithm then goes from word to word. And for each word, it assumes that the association of this word to a certain topic is wrong, but only of that word. All the other associations are correct. So it's almost like it corrects a mistake. Yeah? And in order to correct this mistake, or this pseudo mistake, it measures 2 things. It measures, first of all, it measures the proportion of words in the document that are currently assigned to the same topic. So if you are in the Bello Gallico chapter 1, and you look at the word Gallia, you're at the first word of the text, you look how, and the word Gallia was randomly assigned to topic 7. You try to measure how many other words are assigned to topic 7. And then you might see that not a lot of other words are assigned to topic 7. So you then measure what would be the best assignment in chapter 1. And you see that most of the other words are assigned to topic 5. And the second most may be assigned to topic 3. So, and of course you could then directly correct it to topic 5, but then the whole process wouldn't work. You would stay in your random loop. You wouldn't really correct the mistake. You need actually another measure to balance the other measure. And the other measure you use is to see how often the word Gallia throughout the whole corpus, throughout the whole corpus Caesarianum, for example, is assigned to topic 4. And you see then, maybe you measure then that's not very often assigned to topic 4, but that's mostly assigned to topic 13, and maybe a little bit assigned to topic 3 as a second. And then, of course, you could say, well, maybe I should then correct to topic 13, but that would be wrong too. Instead, you try to reassign a new topic to the word that both of those scores are optimized. Yeah, so that you probably would then assign it to topic 3, yeah, because that's the second best for the first measure and the second best for the second measure. And that would probably optimize the score. And you do that for every word in the whole corpus you're topic modeling. And then you repeat this algorithm until you have a stable model. So it's almost like a tension that is built between those 2 measurements that helps you to create a stable model if you reiterate the model, if you iterate the model, the algorithm often enough. Yeah, 100% stable it won't B, there's always certain words that jump from one topic to the other. There are certain assignments that jump around, but it's fairly stable. Yeah. So that is the whole theory of topic modeling. That's it. So that's all it is in a way. And when you do that, you can create results that help you for building teaching applications, using them in teaching or using them in reading environments, or using them to find the interesting bits. How do you find the interesting bits in 30 million words of Latin? Well, you could use topic modeling, then see what the topics are you're interested in, and then just automatically retrieve the documents that score high on a topic of your choice. So for example, last year at Tufts University, we implemented the topic modeling results for Thucydides into a teaching application. This is our sight reading application, and the sight reading application helps the students to find similar passages to passages they have already read. So here is a passage, the book 2, chapter 49, the second paragraph in Thucydides, and the algorithm tries to automatically generate side passages. That means passages that should be similar-ish in topic, in theme, and should also determine which words the students have already encountered. And the words that the students have already encountered are here in bold, and the words the students haven't encountered are in blue. And you can click on the blue words, and it would automatically link through to the Perseus dictionary, where they can learn more about the words and find out what it means and how they should pass it and so on. And then they can translate the sentence. So we actually used that to prepare the midterms, to find side passages and unknown readings for the students. And they had great fun. And we told them, you can use this tool if you prepare for 7 sentences for each passage you have read, then you're perfectly prepared for the midterms. That, of course, would be a lot of work. And if any student would have done that, then they would have deserved a good grade as well. So I said in the beginning that it's not really as easy to topic model ancient Greek or Latin as it is to topic model English. And often people ask me why this is the case. And the most honest answer is that the complexity of languages changes over time. If I would be a bit more impolite, I would probably say the complexity of the languages become easier over time. But that's not only impolite, that's also not true. Some complexity in the language is replaced normally with other complexity in the language. So in Indo-European languages, we have the tendency that the languages become less morphologically complex. For example, English barely has 3 cases, he, his, him, and only in the in pronouns. German has 4, ancient Greek has 4 to 5, Latin has 5 to 6, Proto-Indo-European had 8. English, German, Latin have 2 numbers, ancient Greek has 3 numbers. So the morphology becomes easier and easier. It is replaced often by syntactic or idiomatic complexity. So knowing which preposition to use in English is very hard as a native speaker and as a non-native speaker. And knowing that some idiomatic expressions work and others don't, that's another problem. English also has a much stricter word order than Latin, for example. And this is one of the reasons why topic modeling or any other distant learning method that's based on a back-of-words principle works so great for English, because it reduces one of the most complex features of the English language and says it's irrelevant. Yeah? So, but of course, the word order in Latin and Greek is much more free. The morphology is much more complicated. And that brings us to a token frequency. The computer somehow has to know that amicus and amici somehow are the same thing, even if they look different. So, and if we don't have enough instances of amicus, then because it's a statistical process, it won't perform well for this token. Yeah, it will perform well, however, if we tell the computer somehow that amici and amicus are the same thing, or if you throw enough text into the algorithm that this doesn't matter anymore, because then suddenly, if we throw enough latent text into the algorithm, then we have enough instances of amicus and amici, and we can actually differentiate topics that prefer the genitive and topics that prefer the dative and so on. Yeah. In general, we can say that languages flatten as well if the number of speakers is increased. So English is relatively easy to read via with a machine. Yeah, for that reason as well. So there are a number of different solutions we can apply to our data set or to our corpus in order to make it easier and to create good results with topic modeling or other methods. One that is really highly recommended is a robust citation system that helps to combine different analyses with each other. And Monica probably has already talked about the CTS Insight architecture at some point in this SunoikisDC class. So that's pretty much what we are using, and that's really helpful to then run a number of different analyses and then to synthesize them to a more complex philological question. The other thing is, of course, more data. And as I said, we can always throw more data in the algorithm, and that will make our result more robust. And the third method, and that's the method that's also integrated into the topic modeling app you're seeing in a few minutes, it's morphological normalization, where we pretty much try to reduce Latin and Greek words to its dictionary form. A fourth method that I haven't tried yet for topic modeling, but that I could see working is bootstrapping. I'm not sure if you know the story of Münchhausen, of the lying baron. He was trapped in a swamp once, and he pulled himself out on a boot. So and based on the story, statistics came up with the name for adding the same data again into a statistical process. And then they called that bootstrapping in order to address the issue that some of the words do not occur often enough. Yeah? The words here are taken as token. So, and the challenge of morphologically rich languages can be addressed by increasing the token frequency somehow. So it's a token frequency problem. Either the words are not frequent enough, so we have to find a way to make them more frequent. And morphological normalization is one way, more data is another one, and bootstrapping might be a possibility too. So I should say that morphological normalization is great, and it enables us to perform things like topic modeling on relatively medium-sized corpora, like Thucydides text. And but it doesn't come without a disadvantage. So morphological normalization is not lossless. Yeah. So you could use morphological normalization using a parser like Morphois of the Perseus Digital Library, or LetMor, which is a C-based parser that's implemented in TOPAN, and or use tree bank data, where you pretty much have provided by hand by a scholar the correct dictionary form. It is, as I said, never lossless. Here we have an Arabic, classical Arabic topic model. And the words you see here in Arabic are daughter, mother, from her, Fatima, she died, to her, and she transmitted, and so on. As you can see in Arabic, in classical Arabic, you can see in the verb itself, it has a real genus verbus. You can see in the verb itself is the subject is either female or male. And that's great, especially if you have 30,000 biographies and you want only to read the biographies that deal with women. If you don't perform morphological normalization, you get a topic like this, and you can automatically extract all the biographies, all the passages in the text that deal with female biographies. And that's an interesting research question itself, but you lose that when you do morphological, when you perform morphological normalization first. You of course get other stuff then, but you lose this feature itself. So it's often good to have topic models available for morphologically normalized data and morphological unnormalized data, and see what works for your use case or for your research. Just try to think what it actually does and then apply either one thing or the other. So to show you that this is really possible to do that with Latin and Greek, we did actually topic model 30 million words of Latin. And it was on a very dirty-ish data set. The original corpus arrived via Google Drive in over 5,500 text files of various sizes. And I mean various sizes. There were text files with several million words and text files that had less than 10 words. And that's not good. We try to get the documents roughly into the same size. And so we had to perform some normalization as well. When we just looked, split the text up using white space, assuming that the white space is the border between two words, then we had over 30 million words or tokens in a way. Yeah. And if you looked at the how different the tokens were, we had over 600,000 different tokens. So we did some cleaning up. We did some data wrangling. First of all, I removed all small text. I removed all the text that had less than 20 words. Assuming that those words do not help to build a stable model. We can always then build the model and project the results from that words onto the documents, treat them as new documents coming into the corpus. But to build the model itself, I decided to exclude them. And then we were left with around 25 million tokens. What we also did is I split every document saying that it should be at least 20 words, and it should not be more than 400 words, which means all the big text files, and as I said, some of them had several million words, were split into 400-word chunks, pretty much what resembles a page. There are two documents that are bigger than 400 words just because the remainder was under a certain threshold that I decided to link that up with the penultimate 400 words. So we were left with 25.5 million words and almost 500,000 different tokens in over 550,000 documents. So, and that is the resulting topic modeling visualized with the LDA-VIS. And each of this, and we set K, the number of topics, to 100. And each of those 100 topics actually produces something that I, as a philologist, can say, yeah, that is a topic as well. That is one of my favorite ones. It's singularis, numeri, casi, nomina, nominativo, generis, genitivo, and so on. It's a topic about grammar topic from the late antique grammarians, which were also in the corpus we topic modeled. And we can also find interesting stuff. We can visualize how Livy and Virgil look like and how they're structured and which topics they have. And we can see that Livy and Virgil have mainly one main topic. And in Livy, it's bellum, ex ercitum, castra, bello, something about war. In Virgil, it's ama, amis, fata, bella, tela, proilia, something about fighting in war. And it's interesting that the historians and the epic writer uses are talking about the same topic but using different vocabulary, or thematically very similar topic but using different vocabulary. And I was wondering if this is the case in general. And yes, it is the case in general. You can see that here, where we have different history writers, Caesar, Curtius Rufus, Nepos, Tacitus, they all score quite highly on this historical war topic. And we have the poets on the other side, Catullus, Horace, Livius Andronicus, Ovid, Virgil, and they score all very high on the poetic war topic or poetic fighting topic. So that's not really surprising, obviously, to any classicist. We know that epic writers and historian writers pretty much write about war with different words. But what about the things we do know a little bit less well? What about the panegyrics, for example, where we can then see how much of a historic vocabulary or the historic topic is this panegyric writer or a speaker, to be precise, using, how much is another one using. And so to calibrate the observations we had about the topics on the things we already know, and then to project them onto the things we don't know that well, that's one of the strengths in topic modeling, and especially when it comes down to the abundance of late antique and Neo-Latin literature. So, and of course, interesting to see there are also orphans. My favorite orphans are people like Plautus or Petronius, that mainly mock things, and they mock a range of things, and they make fun about a range of things, and that's why their topic structure is very diverse. Or people that have a very, very great, huge oeuvre. So we didn't differentiate between Cicero's speeches and philosophy texts and letters, and because of that, we can see that it's a big mix, because Cicero's oeuvre is so wide. Yeah. So to summarize the findings, is that topic modeling has a huge potential, particularly in research that combines quantitative and qualitative methods. We can look at something we already know and then try to deduct from this using visualizations and topic modeling results to make assumptions about the text that we don't know. We can filter according to certain topics and find only the texts that are interested in, only the texts that are fitting our research question, only the texts that deal with female biographies, or only the texts that deal with grammar, only the texts that deal with a poetic description of fighting. Yeah? So, and in order to show you a little bit better what it actually does, the University of Iowa and the University of Leipzig are collaborating on this, and we are currently preparing a survey that's going to launch this Monday, and we will mail it out via the Digital Classicist mailing list, part of other mailing list, obviously. And there you can answer some questions and see some more of the results we've generated in this topic modeling 30 million words of Latin project. So this was pretty much how topic modeling can be used, and how topic modeling can be applied, and what you can do with topic modeling. Now I'm going to talk you through to how to actually use it yourself. And one way of using it yourself is using MORPHOLOGICAL. MORPHOLOGICAL is an open source application written in R. It's free. It's published on Zenodo and GitHub, and enables you to do topic modeling without any prior knowledge, and to then also explore the results and use the results to do something else with them. It is a topic modeling graphical user interface. That's how it looks. TOPAN is the name. It's a bit of a play on words. TOPAN, you probably know the Greek principle, which roughly translates to take everything into consideration. So it's based on that. And the logo is a Milete butterfly. So it's the butterfly is only as for Milete, and TOPAN as a name. And because of that, most people refer to it only as TOPAN, but the full name is actually Milete TOPAN. So you have a home screen. The home screen also has some instructions. There's also some news. So if something new comes up, then it's directly fed into. It runs locally. It's not a web application. So you can, you could install it on a server and use it as a web application, but it definitely runs locally on your machine. You can input a number of different data in a number of different formats. The most simple format is probably the CSV format, but I will talk through the different formats in the live application in a second as well. So you import your data, then you do some morphological analysis with it if you want to normalize it. And you have different options of how to analyze it morphologically. You can use the Morphos API that connects to the Perseus server and performs a Morphos request. You can use LATENT if your computer is able to do LATENT. You can use a STEM dictionary that you have fed locally into the process, or you can use a STEM dictionary that is already on the server. Those morphological normalization takes a lot of time, especially when you use Morphos. For example, when you want to normalize the Thucydides using Morphos, depending where you are in the world, always sending an API request for each word to Boston takes a bit of time, and you probably run the whole thing for 2 hours. Because of that, you can actually save the STEM dictionary, the stemming dictionary you're generating on your machine, so you don't have to connect to Perseus again in the future if you use a data set, a corpus that is similar. Yeah. I will say a little bit about stop words in the live applications, but stop words are the words that a machine, an algorithm ignores. They are often you start with the most frequent words. Here, for example, the 200 most frequent words, and you have words like at, in, known, ut, at, cum, and so on in it, and it's really clear that those are words that do not contain a lot of content information. And that's why it's good to actually ignore those words, because they just skew a little bit with the algorithm itself. This is the topic modeling interface itself. I changed it slightly. Instead of bars, you actually type in the number now, which is much easier for the user. You select your corpus, you select your stop word list, and then you select some of the features and you start the process itself. But also this we will talk quickly in the live demonstration in a second as well. And then you can explore and export this. Yeah. I think before we go into the demonstration of TOPAN completely, maybe I should take some questions, if there are questions, also to check with you if I've stopped the screen sharing for a moment. Check, okay. Check with you if...
yeah, there are questions. Yes, Anise from Brazil.
Okay, just a doubt. When you say different tokens mean the same of types, or tokens are associated to lemmata. Well, token is always what you want it to be. So TOPAN tries to do word tokens, yeah, and it generates 2 corpora from your corpus if you do morphological normalization. A corpus reduced to the dictionary form and the original. And when you feed the original corpus into the topic modeling process, then it will use the original words as tokens. If you feed the normalized corpus into the topic modeling algorithm, then it will use the dictionary forms as tokens. That's completely independent though from topic modeling itself. You can use as token whatever you want. Words, however, are great because they help you to interpret the topic model later a lot better. You could always use character engrams. You could, and it would generate a great stable model, but it wouldn't be obvious directly for you as a human being to interpret the model. And then it might be better to use different methods to do the distant reading itself. One of the great advantages of topic modeling is that you can interpret it easily and quickly as a humanities scholar. Does this answer the question? I hope. So token both in a way. Yeah, okay, good. Are there any other questions? Did everybody understood the principles of the LDA algorithm roughly? How it stabilizes with the two measures and then creates a stable model? I take silence as a yes.
Okay, yes.
Okay, good. Should we maybe proceed to the, I have two more slides that talk about the installation of TOPAN. And then I go into TOPAN itself and explain what you can do with TOPAN. Would this be a good way forward?
Yeah, excellent. And then I can see the chat. So if there are questions, I can interrupt you and
yes,
people to ask questions. So don't worry, Thomas. Yes, I
okay,
can do that.
because I can't see anybody while I'm screen sharing. And the other thing is, if you're a little bit overwhelmed, just try to do the exercise and send me an email if you have any questions. The last time I introduced TOPAN, we had 2.5 days of workshops. So doing it in an hour is probably very stressful to you as well.
It's challenging. Yes, we know.
Okay, good. So let me talk you through the installation process. I didn't share screen, so let me start with sharing screen again. Good. Okay. So, as I said, it's open software. And if you go to Zenodo, which is the great repository managed by CERN, you could search there for TOPAN and you would find it. Another way would be to go to my GitHub account. And so the GitHub, the link is also in the slides. So you could just copy paste it later into your browser. So if you go to github.com/thomask81/TOPAN, you get to that page here. And this is something that's always true for all free software on GitHub. You either have the option to clone or to download a zip file. Yeah. Since you don't really want to contribute to TOPAN, or maybe if you want, clone it, but downloading it as a zip is absolutely okay. Yeah, and then just unzip it into a folder of your choice, and then you can actually use TOPAN if you have if you have the programming language R installed. So, and that's the other important bit. On this page, under the hashtag installing it, is a short description of how you actually install it. And I try to make it as easy as possible. Yeah? You have to install R, which is a programming language, or some refer to it as a statistical environment, but it's actually Turing complete, so it should be a programming language. And you can also install something that's called RStudio. And this is RStudio. RStudio is an IDE, an interface that I use in order to program R code. And TOPAN won't work if you haven't R installed. RStudio is optional, it makes things nicer, but R is the thing you really need to install. So once you have installed R, you have to start up R. It's often just done by typing the letter R in your desktop environment, no matter if you're in Linux or Windows or Mac. And then you copy and paste this one here. Yeah, from install packages, Shiny to ggplot2, you just copy and paste it into your running R session and execute that. Then you say library Shiny, and then you type in run app, and then wherever the path to the zip file you've just unpacked, yeah, the path to the unzipped zip file. And this link, this folder structure should link to a file that says app.r, yeah? And then you just execute that and you will get into TOPAN. So it will open up in something that looks like this, and then you can click here on the little thing that says open in browser, yeah? And once you do that, it opens in a browser of your choice. My standard browser is Opera. So for me, it opens here in Opera. So, I just pop it up a bit so people can see it a bit better, what's going on. You have a menu bar here, and here you have some description of TOPAN. Here, as I said, you have the news, and if you get accepted on a conference and you tweet about it, and you're using TOPAN, then I will include you into those news things as well. You have some instructions on data entry, how to use TOPAN. So if you, on morphological normalization and so on. So if you get lost, especially in the beginning, that might be a good section to start, yeah. So as I said, I told you that you have plenty of options to import your data. I should probably restructure the menu a little bit because the easiest formats are here. And the formats that are most known to you are probably CSV, which is just a table, or treebank XML. I'm sure you all are familiar with treebank XML. So you can upload treebank XML into TOPAN, and you can upload CSV into TOPAN as well. Those things here are a little bit more tricky. The CTS API is the Persates Capitans API, where you can directly link with Persates text and retrieve Persates text. But again, it is pretty much one request per document, so it can take quite a while until you actually have requested everything. Local Capitans is the same API, but a local installation of it. Thibaut Clarice made it possible that everybody can install a local CTS and local Capitans version. You can use it into TOPAN. Server-side RDS is a binary format that is used by R, and it just helps you to find what's already on your server. So I can retrieve quickly a corpus that is already on my local machine and check what's in there before I use it for topic modeling. Yeah. So if you have imported a text using one of those things, it will automatically generate an RDS file, and then you can reuse the things that are already uploaded. Yeah. So let's start with the easiest one. Let's import a CSV file. And the CSV file I want to import first is a simple table file. CSV is comma-separated value file. So you have identifier, comma, text as a heading file, or maybe you don't have a header. You can actually, if you have a headerless table file, you just untick this box. Yeah. But let's assume you have a header that says identifier and a text or whatever, and then you have an identifier on the left side and the text content on the right side. So let's import some Petronius maybe. So documents, TOPAN, Petronius CSV. So, and this one doesn't have a label, so I actually have to, and I know that the separator is a comma, but I also have the option to have a tab separated file or a semicolon separated file. But this one has a comma separated file. And I say a label no, and then I submit it, and now it's ingested in TOPAN. Yeah. There are other options. I could generate labeled Petronius, And if I would just do it now, I would say can't assign two names to a 3-column data table because this file actually has a label. So if I click yes, then I can see the table file with the label itself. Yeah. So and I could search for instances that have Köntges in there or something like that. So it's fairly simple to use. The funny thing is about, is that a question?
Thomas, one thing, I have your screenshot here, and so we can see the 3 columns. Just to summarize for people, because you're presenting many things together. Of course, in the first column, we can see the identifier, the CTS URN for identifying this passage. We know these things in Sunoikis, we have talked about that, but just to summarize this for people. And in the third, well, then we have the text in the second column, I see, a specific passage, in this case, yes, of Petronius, and the label. How do you produce this? How do you, maybe I missed that, so I'm asking this.
No, it's already, you didn't miss it, it's already produced. So
how? Okay.
Well, however you want to produce text in a way. You can use Excel to produce it. You can take your text and put a table. In the first column you put all the identifiers, and the second column you put all the text.
Yes, but basically is a manual work in the sense that you assign labels to each, I don't know, paragraph, chapter, or section of a work. I don't know if
yes.
Okay.
Yeah. So whatever you want your documents to be.
Okay.
So you have your corpus, and you chunk this corpus into documents.
Okay.
And you have to tell the machine somewhere what the chunks are.
Okay.
And on the left side, it should be an identifier. And you will have the most fun with TOPAN if you use a valid CTS identifier. Mm-hmm. It works with any identifier. So locally, what TOPAN will do is it will create, you can see my folder structure now.
Yes, we can.
What TOPAN will do is it will try to put the data under dub data, yeah, and then it will use it will try to pass the identifier itself like a CTS URN, which means you can then follow this structure in order to retrieve the corpora that are already read into TOPAN. So if you don't have a CTS URN, you will still get stuff done, and you can create like pseudo CTS URNs, but it's most likely that your corpus will end up under NA, yeah, because it can't pass the identifier itself. So it's a bit tricky-ish, yeah. So all you need for TOPAN to work is a table in the format 1 column identifier, the other column is text, and it's your decision of how you structure it.
And the label is part of the first step for associating topics to words, because at the beginning you mentioned this, so we have to start associating topics to words, and then of course step by step we can refine this.
The label is optional.
Okay.
You use either a 3-column table that has a label, or you use a 2-column table that has no label.
Okay.
And you tell TOPAN here on the left side whether it has a label or not.
Okay.
So the label is quite handy, because what TOPAN does is it will produce it will in fact produce 3 corpora if you have a labeled CSV file. It will produce 1 corpus that has all the text, and 1 corpus, well, it depends how many labels you have, at least 3. Here in this text we have Kena and not Kena. So is it either Kena trimarconis or is it not of the Kena trimarconis? So it produces 1 corpus that is not the Kena trimarconis, 1 corpus that is only the Kena trimarconis, and a 3rd corpus that is everything. So that helps you if you have a bigger corpus. you might be interested in only topic model parts of it. And that way you can topic model parts later in the topic modeling process itself. Yeah?
Okay, thank you. Excellent.
Yeah.
Thank you.
Yeah. So producing a CSV, should I maybe show a CSV file as well? Just to be, so the easiest way, the easiest input format is this. Yeah. We have identifier and we have text. So that would be the easiest input format for TOPAN. Yeah. TOPAN deals also with other input formats, for example, treebank XML. You guys should probably know treebank XML. I have an example here. This is, as you can see, treebank XML. I have the sentence, the ID, and I have some kind of tagging and all of this. And TOPAN can deal with the treebank itself. Somewhere, so I have to just restart the app somewhere. Was hooking. Okay, so data input treebank XML. So here we have the treebank, and to submit that, let's read in the text, and here we have the Iliad, yeah, Menina, Edithia, Peleado, and so on. And you can see that another handy thing about treebanks, especially for poetic text, is that the CTS URN is often not good because a verse is not a logical chunk of text content-wise. For the verse, yes, but not for the content of the text. And so it uses, it creates the documents using the sentences generated in the treebank XML. And here again, what TOPAN is doing in the background, it's creating actually two different corpora. Let me show you the different corpora. So server-side RDS. Homer is TLG. Yeah, that should be. So you see that one RDS corpus here is it's just called treebank, TLG 012, TLG 01 treebank, and that one is treebank path. So if I click on that one, you can see I have Menina, Edithia, I have the Iliad as we all know them. And if I go in this corpus, I have Menis, Aido, Thea, and so on. I have the dictionary form. So TOPAN is taking out of the treebank XML file both versions of the text, the parsed version and the unparsed version. And you can then choose what you want to topic model. Yeah. And of course, sorry Thomas for the parentheses, this is for our audience in general, the identifier, as you can see, the substring allows you to select the text you want. Yeah. Yeah, exactly, in the CTS URL, yeah. Yeah. TOPAN ignores that. I should be quite precise. For TOPAN, it's just important that there is an identifier that has this name, but it actually doesn't do anything with that. But these are the substrings in the CTS, yeah. Yeah. And technically, I should probably give it another identifier because that is now a different analytical exemplar. If we would be like 100% CTS correct, this identifier itself should change, but I don't want to make it too complicated for the user as well. Yeah. So I think treebank XML might be actually the handiest way to import your data. So let's now do something with your data itself. The morphological service takes a tiny bit longer, but I show you what it actually does, just to show it in action. You can, if you don't have a treebank XML, but just a normal LATENT corpus in a CSV format, and you just have read it in, then you might want to parse it. So for example, we have our Petronius corpus here. Let's just look at the Kena because it's a much smaller text than the rest of Petronius. and use LATMOR for parsing. In order to use LATMOR, you actually have to install it, and it's on the TOPAN webpage of how to install LATMOR. I should say it only works for Unix systems, so only Mac and Linux users can use LATMOR at that point. I'm sorry about that, but I did not write LATMOR itself. All other users have to use the Morphos API, and you still get good results. The Morphos API is just a lot slower than LATMOR. So I have the Kena text, and I want to parse it, and I give this dictionary also a name. I can say Petronia stemming dictionary, yeah, and then I submit it. And now the computer automatically, you can see it on the right side, tries to parse all the words, all the unique words that are in the text. And as I said, it's fairly, that's speedy compared to Morphos, but we would probably still sit here for probably 2 minutes until it's finished. So I will just end that and restart TOPAN. Yeah. But that's the way the parsing itself works. And you can use, as I said, Morphos API instead. Once you have done any of those things and you have saved your dictionary, you can use either by selecting a stem dictionary that is a CSV file here, or you can automatically, Morphos is also generating dictionaries, and you could generate the LATMOR stem dictionary or the other dictionary here as well, and then do that automatically. For example, if I have the Kena again, and I use that one here, and I just submit it, then I get a bug. Sorry. Okay. This one doesn't work. Okay. That's always a problem with live demonstrations. There's one thing that doesn't work. So Morphos API and so on works, as you can see, and you can see now how much slower Morphos is compared to this LATMOR. And the reason for that is just simply that it sends API requests across the Atlantic while I'm in a Google Hangout, so it's probably also not the best way. I will stop that again and restart the app. Yeah. So good, but you can do that, and you can save it, and yeah, and I will fix the bug in the next couple of days, and then you can redo the parsing easily. But once you have done the parsing itself, you always have different texts, as you say, tree bank parsed, but I also have a text that, yeah, LATMOR parsed, for example, that would be the Petronius Satirica parsed with LATMOR, and I just want to generate 200 stop words. And maybe 200 is too much for this text, so I generate only 100, and then I have 100 words, so the 100 most frequent words. And I can see that Trimalchio is here, and I might actually be interested in Trimalchio, so I want to remove Trimalchio from the list, and I can just type it in here to remove words from stop word list, and Trimalchio is removed. That was particularly important in the University of Iowa, where people looking at church literature, and Jesus obviously was the stop word, and Paul Dilly asked me to remove Jesus, and I said, well, but it's a stop word, and he just answered, but it's Jesus, man. So sometimes we just have to remove stuff, and it might actually help to interpret a certain topic. There's also some frequency of words is just an indication of things are stop words or not. You might have additional stop words, and you could type something like Thomas in here if you want to remove Thomas from your corpus. What probably is a more frequent stop word in your corpus, depending how dirty your text is something like this. For some automatically generated corpora, you might have TEI header as a stop word, depending on how you generated the text itself. So those stop words are also automatically saved, and they will help you to actually do the topic modeling later on. So let's do a quick topic model of the Satirica itself. So as I said, this is following CTS identifier. The Satirica, maybe we just go for the Kena text because it's, no, let's do all of the Satirica. And I choose a stop word list, and I want to have the 100 most frequent stop words. As you can see here, again, the identifier is used to save the stop word list as well. Here is Petronius, Satirica, most frequent words 100, and I select that. TOPAN saves your model into something that's called a CTM file, which is also a text file that has all the information. And that then helps you, if you want to use the tables and so on, you can use the tables itself. SunoikisisDC, SunoikisisCTM. The .ctm comes automatically. And occurrence threshold, here I can tell the algorithm to ignore every word that occurs less often than 3 times. I can set it to 2, I can set it to 100, that wouldn't make any sense. I put it to 2 because the Satirica is a fairly small text, it's only 30,000 words. The seed could be a random seed. This determines in the beginning what the, which association the words have in the beginning, which assignment. I set the seed so you can redo the model and get the same result. If you want to see how stable your model is, you can change the seed yourself. Yeah. The number of topics, I want to see 20 topics, but I could change that to 12. Let's do that. Alpha and eta are hypervariables, and they're set by default to 0.02. And while you can change them, there's some reading going on while they're set to that. You can use the advanced reading set on GitHub and then follow the links there as well and decide for other hypervariables. But so you can change that as a user, but most of you probably won't change it as well. Number of terms shown doesn't say anything about the model itself. I set that to 40 now, just for the visualization. And the number of iterations is how often you let the algorithm run through. You will, with 500 iterations, you will get a fairly stable model. You can set it to 2,000 iterations to be on the sure side. Here we just set it to 100 iterations because each iteration, of course, takes time. So let's run that. And it's topic modeling, it's structuring the results, and that's done. So now I can see my text again with the 3 columns. That means that the model has run through. So you actually want to have a look at the model itself, and this you do on this tab, in the LDA this tab. And there you can select the model you've generated, and the folder structure is quite telling itself. We have the most frequent 100 words used as stop words. We have set to 12 topics. We have the alpha value of 0.02. We have an eta value of 0.02. We have 100 iterations, and the seed was 73. And this won't be a very meaningful topic model right now, but we could go through it and see what it actually says. So you, in order to have a more meaningful model, you would have to run more iterations. For example, here we have one that is run with 2,000 iterations, and here we have slightly better models. Yeah, consumer, Kinare, Titulus, and so on. Yeah. So Peccare, Lacrima, Mors, Dolor, and so on. Yeah. So the models, the topics make a little bit more sense. They make even more sense, obviously, if you put more text into it. So the Satirica is a bit on the border of how much of what is possible, how small a text can be. What is also very important are the tables, and we have two kinds of tables: the term topic tables, where you can see for your model what scores for each topic certain words have. And what is probably more important to you is the document topic table. Let's go again to the Satirica, where you can see the text itself, and you can see the out of which topic each text consists. So that's so this text here is 37% this topic, and 56% this topic. And it has a simple search function in it, so you can look at all the passages that contain in corpus and see how they're structured. Yeah. There are some basic visualizations. It might be interesting to you to to sort the text according to one topic and then see how another topic compares in comparison. So here, the text would be sorted. That didn't work. The text would be sorted to topic 1, and we have topic 7 on the right side in comparison, and we see there's no correlation of topic 1 and topic 7, but sometimes there is a strong correlation between the two. We had that in Persian literature as well. You can download the corpora you have generated. You can download the tables you have generated, but that is mainly for the server version. Everything you are creating is also under www data. Then you identify, here's Petronius, the different models and the different visualizations. So here I have the visualizations I just saw. Let's open that up with Safari. So here you can see the visualization. Here we have the tables. So the theta tables here. And as you can see here, all the scores for the topic modeling itself, and so on. I would love to have shown you how you can take such a simple table and put it into something like, for example, Google Fusion, but I think we are running out of time. So you could easily, if you know Google Fusion, you could easily take any of those generated tables, upload that in Google Fusion, and generate your own visualizations and explore the data on your own way, again, without writing a single line of code. Yeah.
Okay, Thomas, thank you very much. Yes, unfortunately, it is 6:18, but maybe, I don't know if there are questions. We have people in the Hangout today.
You know, Francesco's doing anything for his project?
I don't know if we have questions. No questions. Well, Thomas, thank you. Of course. Maybe, I don't know, Gabby, if you have a question. I don't know.
I was only going to say, I don't really have a question, but I was going to say that I found this really interesting. It's something that's completely new to me. And I'm only sorry that my students finished their term several weeks ago, so I don't have any students doing this. Partly because I think it would be really cool for them, and partly because having a class of students is what would motivate me to actually work through your examples in more detail and make this work, which I may not be able to motivate myself to do in the next couple of weeks otherwise, because there's always so much on. But I very strongly intend to use this video as a substitute for a live session, when I get students again next semester. So thank you. This was really, really interesting.
Yeah, you're more than welcome. People in the University of Iowa mainly saw that also as something that where undergraduate students can directly produce results and also can easily understand the concept and learn stuff about it. If you use it and you do the exercise and you have any questions, just flick me an email and I will try to answer that. As I said, that was 2.5 days in an hour. So it's maybe a bit too much.
No, of course, and the goal of this session was to be a first introduction to topic modeling, which is of course a complex topic, we need more time, but we will have other SunoikisIS Digital Classics semesters, so I'm sure, Thomas, that you will be back for other sessions, so our community can learn step by step how to use topic modeling, but we have your class outline, your tools, of course, and thank you for being available for questions. So now, unfortunately, I have to finish, but this was our last session for this semester, long semester. We had 23 weeks, and of course, I have to thank you all for participating in SunoikisIS Digital Classics. First of all, Gabriel Bodar, who helped me to build this syllabus, and of course all the participants of the planning seminar we had in Leipzig last December. And well, we will have soon in September another SunoikisIS semester led by Gabriel Bodar in London, like last year. So we will have our usual fall semester, about 12 weeks, and then of course again a spring semester in 2018. And we will post information about that. Of course, you know that we have our website in Leipzig, but in GitHub you can find information about everything. So thank you all. Yes, yeah.
Very slight correction to the fall semester.
Yes.
The fall semester, which is SunoikisIS Digital Cultural Heritage, I think we've decided we're going to call it this year, will likely be run by Rada Varga and Tom Elliott, and assisted by me, but we shouldn't let me take too much credit for it. And it'll be 16 weeks. It'll run until the middle of January.
Okay, excellent. So thank you very much, Gabby, for this. So 16 weeks, great. So we have another long semester, and we are very happy to have both Tom and Rada, who is in the Hangout today. So our community is growing. I'm very happy about that. But now we have really to finish our session. So thank you all for this semester. Thank you, Thomas, for this great last session.
Pleasure.
And so enjoy your summer and see you in September. Bye.